Every single time you board an airplane, the same ritual plays out. A flight attendant stands in the aisle, gesturing toward the exits, and you completely tune out. You've heard it before. You know where the doors are. But here's what you probably never thought about. Those big boxy panels at the bottom of every airplane door. You've walked past them hundreds of times, maybe thousands, and you've never once asked what's inside. What's inside is one of the most aggressively over-engineered safety devices ever built. Something that takes skilled technicians 2 full days to fold by hand, that explodes into a 2-story ramp in 6 seconds flat, that can hold the weight of dozens of sprinting humans, survive fire, shrug off gale force winds, and in some cases detach from the airplane and become an ocean life raft. And the reason it exists, because people used to die. Not from plane crashes, but because they couldn't get off a perfectly intact airplane fast enough. Let's start with what most people get wrong. If you picked an emergency slide, you're probably imagining something like a bouncy castle at a county fair. A big inflatable ramp. Simple, right? Just a slide. That assumption misses the point entirely. The problem emergency slides solve isn't how do passengers step down from a high door. The real problem is this: how do you evacuate 300 panicking human beings out of a smoke-filled metal tube in pitch darkness in 90 seconds when half the exits might be completely engulfed in flames? That 90-second number isn't arbitrary, by the way. It's a federal regulation. The FAA requires that every commercial aircraft with more than 44 seats must prove it can be fully evacuated. Every passenger, every crew member, in 90 seconds, in the dark, with half the exits blocked. That rule exists because crash investigators learned something grim. In most survivable crashes, the impact itself doesn't kill people. Smoke does. Fire does. Drowning does. And every second a passenger spends trapped inside the cabin dramatically increases their chance of dying. Before inflatable slides, the options were horrifying. In the 1940s and 1950s, airliners used knotted ropes. Then came flat fabric chutes, sheets of material that a flight attendant would lower from the door, and 2 strong passengers would have to climb down and hold the ends taut while everyone else slid down between them. Imagine trying that in a fire, at night, with 100 terrified strangers pushing from behind. Then came the disaster that changed everything. On August 22, 1985, British Air Tours Flight 28M was taken off from Manchester Airport when an engine ruptured and caught fire. The pilots immediately aborted. The plane never left the ground. It should have been completely survivable, but 55 people died. Most of them didn't burn. They suffocated. Toxic smoke from the cabin materials filled the fuselage in minutes. 1 exit door. Jammed because of a design fault in the slide system. Passengers crushed together in a passageway barely 22 inches wide. The investigation called it a defining moment in the history of civil aviation safety. It triggered sweeping reforms, fire-resistant seats, floor-level emergency lighting, wider exit rows, and it cemented the principle that evacuation systems aren't optional extras. They're the difference between everyone walking away and dozens of people never walking again. So what does a modern emergency slide actually look like under the hood? Because the engineering is genuinely extraordinary. Start with the packaging problem. You need an inflatable structure roughly the size of a small room, rigid enough to support dozens of adults running down it simultaneously. And it has to fit inside a compartment built into the aircraft door. The packing process takes specialized technicians approximately 2 days per slide, and it's been compared to packing a parachute. Every fold matters. One mistake and it won't deploy correctly when someone's life depends on it. Now, the inflation. This is where it gets clever. Inside the slide pack, there's a compressed gas cylinder, CO2 or nitrogen, roughly the size of a soda can. But here's the thing, that tiny canister doesn't contain nearly enough gas to inflate the entire slide. Instead, the gas blasts through a device called an aspirator. The aspirator uses something called the Venturi effect. When high-pressure gas rushes through a narrow nozzle, it creates a vacuum that sucks in enormous amounts of surrounding air. The canister provides the initial punch. The atmosphere provides the volume. It's a multiplier. That's how something the size of a Coke can inflate a structure the size of a room in 6 seconds. And those 6 seconds, that's the modern requirement. Back in the 1960s, slides had 25 seconds to inflate and only in calm, mild weather. Today, they must fully deploy in 6 seconds in temperatures ranging from negative 65 to 160 degrees Fahrenheit, in crosswinds up to 25 knots. Think about that. A device that's been sitting dormant inside a door for potentially years must work flawlessly, instantly, in Arctic cold or desert heat, in a howling crosswind, every single time. There is no second attempt. The slide itself is built from urethane-coated nylon sprayed with an aluminized fire-resistant coating, because when you need an emergency slide, there is very often fire nearby. It contains at least 2 independent inflation chambers. So if one loses pressure completely, the other still supports a full evacuation, and the surface is carefully calibrated to flex under different body weights. Fast enough to move passengers quickly, slow enough that a 70-year-old grandmother doesn't break an ankle at the bottom. But here's the part that really got me. Once you understand this engineering philosophy, build. Something that sits dormant for years and must work perfectly in one critical second. You start seeing it absolutely everywhere. Your car's airbag is the most obvious example. Same core idea, compressed gas, an aspirator to multiply volume, a structure that deploys in a fraction of a second after sitting inactive for the entire life of your vehicle. Both systems get exactly one chance. There is no retry button, but airplane slides go further than airbags. Many of them aren't just slides, they're slide rafts. In 1965, a Qantas safety superintendent named Jack Grant invented a device that works as an evacuation ramp on land and then detaches from the aircraft to become a fully equipped life raft on water. One single piece of equipment complete with an erectable canopy, paddles, leak stoppers, and signal flares. It's an inflatable bridge that transforms into a survival vessel. 2 completely different functions, one device. You'll find the same thinking in military ejection seats. Systems designed to function flawlessly after thousands of hours of dormancy in one violent second. And in some skyscrapers, which use vertical inflatable evacuation tubes, essentially airplane slides turned upright, to evacuate occupants down dozens of floors. The numbers make the real-world impact impossible to ignore. A single Airbus A380 carries 16 emergency slides that enable all 550 passengers to evacuate in under 90 seconds. Its dual-lane slides are rated for 70 passengers per minute. Each slide endures 150 to 200 deployment tests before it's ever certified to sit behind a door. And these systems deliver. In 2005, Air France Flight 358 overran a runway in Toronto and burst into flames. All 309 people on board escaped. Most of them were off the burning Airbus A340 within 52 seconds. In January 2024, Japan Airlines Flight 516 collided with another aircraft on the runway at Tokyo's Haneda Airport and was completely consumed by fire. All 379 passengers and crew survived, evacuating through just 3 of the plane's 8 exit doors. Every person on those flights walked away because of the engineering packed inside those boxy panels you've never looked at twice. But no engineering solution is perfect, and emergency slides come with real trade-offs. For one, accidental deployments are disturbingly common. Airbus estimates 30 to 40 inadvertent deployments happen per year across its fleet alone. A single accidental deployment costs between $30,000 and $70,000 just for the slide. And when you factor in canceled flights, rebooking, and passenger hotels, the total bill can approach $200,000. The North American airline industry loses roughly $20 million a year from accidental slide deployments. In one particularly expensive incident, a running jet engine ingested an inflated slide, costing the airline $650,000. Then there's weight. Every slide adds pounds to the aircraft, and pounds burn fuel. Engineers are in a constant arms race to develop lighter, stronger fabrics. Because a few pounds saved per slide, multiplied across 16 doors on a wide-body jet, translates into meaningful fuel savings over the aircraft's 30-year lifespan. And the 90-second rule itself is facing hard questions. The standard dates to the 1960s and was originally tested with fit, young volunteers. No children, no elderly passengers, no one in a wheelchair, and no carry-on luggage cluttering the aisle. Real-world evacuations don't look like that. Japan Airlines Flight 516, despite being a success story, took a full 18 minutes. Congress has since passed the EVAC Act, requiring the FAA to update its evacuation testing to reflect what passengers actually look like today. So let's go back to where we started. That boxy panel at the bottom of the airplane door, the one you've walked past 1,000 times without a second thought. It contains a device that took decades of tragedy, engineering brilliance, and regulatory reform to perfect. A machine that compresses 2 days of hand packing into 6 seconds of life-saving deployment. That functions in Arctic cold and Saharan heat. That can be a ramp on concrete in a raft on the ocean. That has been tested hundreds of times before it ever sits quietly behind that door, waiting. Next time you board a plane and hear the cabin crew call doors to automatic and cross-check, you'll know what that actually means. You'll know what's hiding inside those doors. And you'll know why the engineers who build these things say they hate to see them used, but feel immense pride when they work. Here's the question I'll leave you with. What other piece of everyday engineering are you walking past every single day without ever asking why it's there?